Hello everyone and welcome to our webinar, The Emerging Technologies Behind Intelligent Self-Service, a presentation by SunView Software for BrightTalk's Emerging Trends in ITSM Summit. My name is Jamie Spector, the Product Marketing Manager here at SunView Software. I'll be your host for this presentation. And for your main event speaker is Dr. Lawrence Hall, a distinguished professor of computer science and engineering at University of South Florida. Dr. Hall has authored over 190 publications in journals, conferences, and books. He has received funding from the National Institutes of Health, NASA, DOE, the National Science Foundation, and others. His research interests lie in distributed machine learning, extreme data mining, bioinformatics, pattern recognition, and integrating AI into image processing. Larry, we're really excited to have you here with us today.
Thanks, Jamie. I'm glad to be here and looking forward to giving my presentation.
Excellent. Okay, so before we get started, I just have a few housekeeping notes. So this webinar will be available shortly after its conclusion. Be sure to share this webinar and check out any of the supplemental content, including in the attachments panel of your module. And if you have a question regarding anything that is covered during this webinar, you can use the Ask a Question button at the top of the screen module to submit your question to the webinar panel. So just a quick agenda. We will be getting started with Dr. Hall's presentation, followed by a summary and recap, and then just a few minutes of AI for ITSM and self-service, some real-world applications of those, a quick spotlight on our product change gear, and then a final brief Q&A. So our goal today is to have everyone leave with a better foundation for how AI and machine learning technology helps to improve IT self-service, support operations, and more, and how these concepts are being implemented today in the real world. So one last thing real quick. We have our supplementary ebook available, as I was saying. It's the 7 reasons for why AI will change everything on your service desk. It kind of goes into, some AI and smart automation more applicable to IT service management. So without further ado here, I'm going to pass it off over to Dr. Hall.
Thanks, Jamie. Hi, everybody. So I'm going to give a little background on how emerging technologies are helping do the self-service kind of work, with a particular emphasis on deep learning. So machine learning is the overarching concept of taking data and building models. You can have 2 types of models, well, more than 2 types. So you can have data that's labeled, and you build models from the labeled data. It's usually predictive kinds of models, but it doesn't have to be. It can be actually controlling your car. And then there's unsupervised learning, where you have no labels, and that might be things like somebody predicts, if somebody purchases certain things at a large online retailer, I guess that they're going to get other kinds of purchases because I've seen other people purchase other things when they purchased whatever was purchased now. If they purchased a bowling ball, and I've seen them often get gloves for bowling. That obvious kinds of stuff. And I'm going to focus on supervised learning, where we actually have labeled data. So I think that in self-service kinds of things, you can collect a lot of data. You can, and probably some of you already have, big corpuses of data with labels on it. You know that these kinds of problems have happened, and these are examples of them. And machine learning works well when you have good data, and by good data I mean data that has good labels, so the labels are correct, but also isn't tremendously noisy. So if I have features from that data, if I've extracted features, there is not a huge amount of noise. I don't get the really wrong signal there. It actually turns out that a little bit of noise on the features is okay and actually can be helpful, because all of machine learning is built on the idea that everything is independently and identically distributed, which means that your training data is going to be the same as your test data. Unfortunately, that's not ever the case, but in order to do any of the math, we have to pretend, and that's why having a little bit of noise in the training data makes you not focus so tightly on it, and you'll do a little bit better on the test data. So if we have this good data, we can build models, and we can build models for lots of different kinds of things, and I'll try to touch on those of interest as I go through this. All right, so you might say, well, what's this, machine learning? I haven't heard about machine learning, but I know about predictive analytics and data mining. Well, or data science, right? They're all more or less the same. I mean, perhaps you know about data science and you want to argue that no, data science is different. I'll grant you there's some differences, but in all of these kinds of things, we're talking about building some sort of model, picking out some sort of information from the data, and doing something with the information that we've managed to get out of the data, right? And today, you cannot go anywhere without hearing about deep neural networks for a very good reason. I mean, a lot of times it's actually shortened to deep learning. I like to sometimes say that I'm not sure what the question is when somebody asks something, but I do know the answer, and it's deep learning. But that's a tongue-in-cheek answer. It does not solve all problems, but it does solve some problems that are, have been out in the field for a long time of artificial intelligence, machine learning, and have not been solved well before. So how come these things have suddenly appeared? It's really, they've been around for a while, and attempts to use them have been around for a while, but in 2012, there was kind of a convergence of people had collected a lot of data, and people realized that you could really do a lot of computation with graphics processing units and build really big models. And what is deep neural networks or deep learning really good at? Well, they're really good at dealing with images, dealing with text, and dealing with audio data. And we have a lot of that data around. The two places that I think you might know of that are of most interest, or we drove the original attempt to develop these deep learning models, is the problem of repeated pictures. So Google and other search engines would have 500 pictures of a cat because everybody liked it and they copied their own cat. But this means you have a lot of storage, and you'd like to know that that's just one cat. So if you can identify it and just have one pointer to a cat, yay, very good. And I'll say some more as we go further along about particular applications. If you think about self-service kinds of things, you're going to have problems that are going to be the same, misunderstandings that are going to be the same, and people will come to them perhaps through different paths, but the end solution will be, with tweaks, very similar. And if you're encountering, I'm sure all of you that have used software have had a crash of the software. And as a computer scientist, I like to think that these were not developed by computer science students. But in any event, you know that a lot of times the application will come and say, sorry, we have to close. Too bad for you, but we'd like to send a report to whoever makes the software. And that's so that they can get information on the problem so that they can fix it at the end of the day. But they can also mine that data to get if they get enough reports and they have enough information about what's happening to figure out how to prevent it. They do a little data mining themselves. But you can collect a lot of data over time. I'm not saying that for those software problems they don't necessarily build a model because hopefully they fix it, push out the fix. You can't fix some of the things that people have to ask about things that they're doing because they just don't follow for whatever reason. So your data can be from emails, it can be from text chats, it can be audio. All that is really great for deep neural networks. They're really, really good at audio also. If you've ever used Google Translate, if you use Google Translate in the early days, you'd get stuff like my French cousin would write to me and he'd say, he told me his daughter was going to school in Cambridge and riding her bicycle around Cambridge, and he writes in French, and I read French so-so, and I didn't know what else he said, so I put it into Google Translate, and Google Translate told me that his daughter had ridden her bicycle across the English Channel, and that's pretty certainly not what he said. But today, I believe it would have told me what he had actually said, which is that she took her bicycle and her stuff and went through the tunnel and a low-cost ticket over to Cambridge to study. And that's improvement from lots of data and deep learning. Now, one thing that I think we all hear is this call may be recorded for quality assurance. And of course, that is a great source of data for deep learning. All this recorded information is something that you can do two things with. If you want to recognize spoken words, you can do that. And in fact, I still, because for two reasons, I know how learning systems have worked in the past, and I'm skeptical if everybody's updated. I don't like to use voice activations when you call into some place and they say, please put in the number that your extension, or say the extension you're looking for. I almost always put in the number. But actually you can say the extension now, and it's really good because they've collected lots of data. And I don't necessarily mean one company. Some company is selling this, they have collected from lots of places, but they can get the numbers 1 through 9 probably almost perfectly for most people. Not everybody. My wife has a little bit of a high-pitched voice, and they still have some trouble with her. But you can also, if you're collecting information about problems that people are having, you can learn to recognize those problems. Maybe you're already using a speech recognizer, but then you build up the corpus of the things that have happened that people have said, and what problem it was associated with, and then you can build a model, and you can actually have a chatbot perhaps respond to this problem that people are having. All right, but if you want to start out, you think it's really cool to build a model to help with service problems. How do you do that? And you didn't store all your data. You have a little bit of data. Well, you don't have to use deep neural networks or neural networks. You can use what my students like to call classical techniques. I kind of rebel at classical because Sparse Vector machines are maybe from the early 80s. So it seems not that long ago. I think of classical as maybe from the 1800s or something. But they work well with small amounts of text. And you could use random forests, which are decision trees, which are really fast to build. If you have good features, they will work really well from small data sets, and they're decision trees that are built into an ensemble, which means a group of decision trees. And so you can use these approaches and actually get often very good performance, maybe not as good as a human, but if you have a human backup for the problems that they can't deal with, it can be just perfect and be helpful. And in the meantime, you can gather more data. So why, this next slide says, why deep learning with lots of data? Why do I say, if you have little data, don't use a deep learning, deep neural network? Some of the earlier work on deep learning, so this is early because it was done in 2013, not that early, but they worked with images, and they built networks that had as many as 40 million weights that you had to train or tune in them. That's a lot of things to tune, and if you have some mathematical background solving optimization problems and go back to the very, very kind of basic stuff of I have n unknowns, I need n equations to solve it, and say, boy, I would not, ideally like to have 40 million examples to take care of these 40 million weight variables. Even with images, that's not happening. even smaller deep networks will tend to have, not tend, they have a lot of weights, right? One of my students was very proud of himself because he built a deep neural network that worked pretty well, one state-of-the-art for what he was doing, and it only had 85,000 weights. But he didn't have anywhere near 85,000 examples, which is why he was trying to build a small network. Now, deep learners are also considered really good for images, for example. They do feature extraction for us, and they can also do that to some degree for speech. For text, maybe not as much. But I tell you, for images, having feature extraction done for you, that's really nice. Now, it's probably not something that you have to deal with. You'd be more interested in something like a recurrent neural network. The really nice thing of recurrent neural networks is they capture the time nature, the temporal nature of language. Sentences have structure. There's a flow to them. And old learning approaches would just look at how many times a word occurs in a document, for example, to categorize a document. And, the order of the words probably does matter, and a recurrent neural network, not probably does matter, it matters. Recurrent neural network will actually be able to take into account the order that the words are coming in order to make a decision, and in fact will generally do much better, so much better that people don't use the old approaches at all anymore if they have a lot of data. All right, so here is a recurrent neural network, and here is a deep neural network. So I've said deep neural networks, deep learning. What the heck does that mean? So neural networks are just things that have inputs and outputs. That's pretty easy to think about, right? And then on these links here that are pointed with arrows going forward, you have weights. So this is a simplified model. I did not put a bias in here if you're a neural network aficionado. But I have weights on there, and what I need to do is tune these weights, right? And if I tune the weights, I will be able to learn a model that could predict a number, could predict a class. Here I have an output layer with maybe 2 classes, and in the middle are what are called hidden layers. So the hidden layers don't have outputs that we know what they should be. So in the output layer, I know what the result should be, and the hidden layers, I don't know what the result should be. In the input layer, I know what should come out of here. It should be the input value. So these are called hidden layers because they're not inputs and they're not outputs. They're hidden layers. Any neural network that has more than one hidden layer is a deep neural network. So this is a very, very shallow deep neural network. It only has 2 hidden layers, but it is in fact a deep neural network because it has more than one hidden layer. So by definition, it's a deep neural network. The interesting thing is the learning algorithm that allows you to deal with 1 hidden layer will allow you to deal with 2 hidden layers, 3 hidden layers, 100 hidden layers. Backpropagation works for them all. So that's great. We didn't have to develop any new algorithms. The other thing that's interesting about this is you have these recurrent links on here. Remember I was saying that you could capture what happens as you go through a sentence. Well, here we have a single recurrence idea. I don't want to make this super complicated. I would like to make it super simple. So imagine that whatever the output of this is, I store it and it comes back to me in the next time step. So that would be enabling me to capture a little bit of what has gone on in the past. I could even have it go for 2 time steps, 3 time steps. It doesn't, there are lots of options. I can have the recurrent links so that I actually pull out the input last time. Here I'm pulling it from the output, but I could pull it from the input. And I don't have to have it everywhere. You see recurrent link here, recurrent link here, recurrent link here, recurrent link here. So the first hidden layer has recurrent links everywhere. The second hidden layer, you see that there's on the top one there's a recurrent link, and there isn't one on the bottom one. You might have looked at that and said, he forgot to draw that. Nope, I meant to do that because it isn't necessary to have it everywhere. So a lot of what goes on with a deep neural network is you have to think about what the right structure would be. So if you're building it yourself, there's a lot of art to it. And there isn't a lot that people can, well, there is a lot that people will tell you about how to artfully develop it, but there isn't a lot that's necessarily going to be true for your application. So this is the kind of thing that goes on. An interesting thing about deep neural networks, about neural networks in general, is that if you have one hidden layer, there's a theorem that says you can arbitrarily closely approximate any function. You can arbitrarily closely approximate any function at all. So that sounds really powerful, and you might say, well, why do I have more than one hidden layer? And it's because while there's a theorem, it doesn't tell you that you can learn to do it. It doesn't tell you how many hidden units you need. It doesn't tell you what the activation function of the hidden unit should be. So you have these things coming in, you do something to get an output value. It doesn't tell you what that should be. So there's some problems with the theorem. It's a bit incomplete. And it turns out that people have had luck with as deep neural networks as deep as 75 to 100 hidden units. And that hidden layers, 75 to 100 hidden layers. This really, really seems like a lot of weights and a lot of work. But perhaps it better emulates the human brain, although the learning in neural networks really has very little to do with human brains, even though they were originally conceived as the units would be neurons. All right, so deep neural networks may have many, many hidden layers. Right, 75 to 100 is possible. Lots of weights to train. If you've got that many hidden layers, you're going to have connections that usually, they're often fully connected. That's probably the default. I think it's fair to say it's the default. So one of the big things that has helped create not a renaissance, but I guess a new era of deep neural networks is the graphics processing unit, the recognition that a graphics processing unit could significantly speed up the training. So GPUs are really very important. Here at the University of South Florida, we have a GPU, CPU supercomputer with 384 CPUs and 12 GPU nodes, each one of which has 8 GPUs on it. And so we can calculate quite a bit very fast. And you need that when you're building a deep neural network, not for the first build of the deep neural network, even though with a GPU, if you have 4 million examples, it could take you, with a fast GPU, maybe, let's say, 4 days to learn the model. But if that model is really good, you're 4 days, who cares? Unfortunately, there's a lot of tweaking that has to be done, so you're going to redo that model many, many times, and that 4 days begins to add up, and you want, as much speed as you can. Without the GPU, you'd maybe talking 3 weeks for each model, 2 weeks, and it gets a little too slow. So GPUs are really important to the deep neural network ascendancy, let's say. And you might say, well, okay, cool. What if I wanted to try something on my data? Well, there's a lot of publicly available software to train deep neural networks. There's examples built into them. And I have listed a couple notable, what I feel are notable examples below. They're pretty heavily used. I don't have any reason to tell you any one of them is better than the other, but I'll tell you a little bit about them here if you want to use them. I note that they're open source, are mostly open source. I believe. So I said mostly open source because it depends on what you want to do with them. If you want to build a network and then do some things that are internal, I think that's fine. If you want to put them into a product, I'm not sure that all of their licenses say you can do that without giving some feedback to whoever developed it. But for just playing around, they're definitely free. TensorFlow is a really nice Python primarily based approach, Python C based approach. Keras is a front end to TensorFlow. It enables you to develop, to generate a little bit of data. You might say, well, if I have 500 examples every class, that's enough to build a deep neural network. It probably isn't. Keras has some ways, at least if it's images, to help you generate data. Piano is another approach that's very nice. MatConvNet for people who like MATLAB and don't ever want to do anything but MATLAB. There's MatConvNet. My only gripe about common, that is, it requires MATLAB, which is interpreted and not that fast, and you pay a little bit of a penalty, in my opinion. I think other people disagree on MatCom. Cafe, I believe it's from Berkeley. They all work quite well, and they're free. TensorFlow has a nice example built into it called with MNIST, which I use for my class, and the set of digits that you learn to classify from a 28 by 28 matrix, just a grayscale set of digits that people have drawn through 0 through 10. All right, so I thought I'd hit a little bit deeper on the deep neural networks idea for natural language. So the natural language could be your written text. It could be audio. You do have to do some processing under what I'm showing you. There are some ways to encourage the neural network to do it for you, but I didn't want to try to do that because we have limited time. So imagine I extract a set of salient linguistic features, and those linguistic features can be words, or maybe they're pieces of sound which encompass words. So if it's text, it's just a word. When you're doing text kinds of things, you want to make sure you don't include words like a, and, the, of. They really don't tell you anything. They're used all over the place. You want to catch words like increase, price, right? If you're doing stock market things, decrease, price, company, problem, right? Those are good. Maybe company, maybe not as good as problem. You want to know the name of the company. All right, so we have some features, F1 to Fk, getting a little technical here. For every feature, you want to create a vector for that feature where it is occurring. So what is it occurring in? And we're going to create vectors with these features, and then we're going to, in the next slide you see, we're going to combine them by concatenating them or summing them or combination into one input vector. So we say, okay, I have this feature, how many times did it occur? So if I go backwards just for a moment, I think I didn't say it as well as I wanted. So this each feature, we get a vector of how many times, basically with how many times it occurs. So let's say the word increase for price increase occurs 3 times. We would record that as a 3 for that feature. And then we want to combine it into a vector. So we can feed this into a deep feed-forward neural network, right? Take this vector of counts. So this is then what's really called bag of words, old-fashioned kind of stuff. Bag of words, how many times does each word occur? Problem with bag of words originally is that when you do it for other kinds of classifiers, you have this giant corpus of words for your vocabulary, maybe 70,000, and any given document has maybe 100 words. Now, you may say, well, wait a minute, are we talking about like really short email messages? Not necessarily, but a lot of the words are what are called stop words, which I was mentioning before, like of, and, the. Don't want them, they don't tell you anything. And if you, step 3 here, combining these vectors can just be handled by a recurrent neural network, takes in the feature, which could be salient words as they come, and it knows that they're coming in order, so you don't even have to create these vectors. You just pull up the features as they come. Perhaps it's just one feature at a time, even in a neural network with 70,000 inputs. And surprisingly, you might actually be able to recognize what's happening there. It's not immediately intuitive to me, but it can work and does work. If you think about text where things are recognized, if you've ever used an article aggregator like Google News, which I use, it does a really good job of putting things today into regional, into national, in grouping articles about a person. So if you have some, I guess, we've had some bad actors that are actors recently, Kevin Spacey, you can find all Kevin Spacey articles located in the same place. And it was done by, it was like, well, not likely, it was done by a deep neural network. How did you used to deal with written text? And you couldn't do it still for small amounts of it, but you had to count, as I was mentioning, how many times the salient words exist, the bag of words, bags of words. It's not as feature-rich, and it certainly doesn't capture the flow of the information. I just get how many times the word occurred in the document. I don't know when it occurred, but I do know it occurred multiple times. It gives you a sparse vector, so if you have a corpus of, say, 70,000 items, you'll have perhaps 100 interesting words. So you have a vector that has 100 elements that are marked with a number greater than 0, and the rest are zeros. So it's a big giant vector of really sparse material. And you might imagine that's not as easy to learn from as capturing individual words as they flow through to a deep neural network, and you would be correct. So where can you use these kinds of things? I was really surprised when I saw chatbots all over the place. I thought, wow, everybody's decided not to staff their call centers, but they're willing to have somebody answer not emails, but answer text messages. That's interesting. But imagine I make that a bot. It takes text or perhaps audio, and after training, it can match to nuanced answers. So I can, say, I want to use this BrightTalk presentation, and what's the best browser to use for that? And it can immediately say, yeah, you should go ahead and use Chrome because we're really well integrated into Chrome, but you can also use blah, blah, blah. I could say, well, I want to use USFX. Doesn't exist, but I could say that, and it'd say, well, I don't know that one, so I wouldn't recommend it. Right, and you can also have this sort of be failover. First response fails, your next one might work, so you stay with the bot, but if the bot continually cannot answer the question or is giving answers that are increasingly causing frustration for the user, and you can pretty easily today build sentiment analyzers so you can see if they're getting annoyed, you can switch over to a human. So, of course, they may get an annoyed user, but at least they can give a better answer. Right, so if you've used a chat window on a website, have you ever thought about it, whether there's a person back there or it was a chatbot? I know on some sites there's a person because they'll ask you to wait, but on other sites I'm pretty sure it's a bot because I've gotten pretty quick responses. And this is kind of a near-term technology for when people have questions. People are doing it. It can be done. So what if you don't have a question, but you have a problem? In other words, you're flailing, right? You're trying to do something with software. You're trying to do something, serve yourself, but you just are failing. And you can have a model that is low power, low energy cost, low compute cost, and it's watching and it says, oh my gosh, I see this person doing, over and over again, this guy is clicking the start button but has not loaded the data to start with. So they just need to be told, load the data, right? And it can pop up and say, hey, if you load the data, this will start. And boy, that'll make for something very nice. I think you fix a problem before you have to have a chat. I believe that will cause some thumbs up from your users. So you will get happy there. Also, if you ask for help in an application, and a learn model can do better than what is often done in the applications that I use today, which is they pattern match what I asked. And if the pattern isn't there, I get like nothing, even though my question can be answered if it's phrased differently. If I didn't ask a wrong question, I just didn't phrase it in exact match for that software. And that's not a hard thing for them to be done, and it will certainly make people happier. So you, boom, help immediately. As long as you know about the kinds of queries and retries, and you stored that, you can pretty, I believe, straightforwardly build a model, and I think some are. Now, of course, if you make your application too slow, that's a different story, but not my problem. I'm a learning person, not a performance person for the model. All right, so this brings me to the end of what I'm going to say. I might have gone a little bit long here. So deep learning can be used to help develop intelligent support systems. If you store up a lot of data, and you'll have the opportunity over time to do that, you can definitely apply deep learning. Deep learning has been shown to be really strong with lots of data. If you want to start quickly to see how well you're likely to get, a model can be built from small data and older learning approaches. So I would warn you that deep learning has provided really significant advances. I used to tell students to run some simple model, and if they got 70%, then they couldn't expect more than 80% on the data. But a deep learning model can give you 20, 30, 40% increases in performance, and has. So, you know, if your small data performance is 60%, you still might reach 90% with a deep learned approach and lots of data. And it's really good with natural language, spoken or written. So I think a lot of support kinds of things deal with language, written, spoken, queries, email, and deep learned systems can be really good. And that's it. Thank you for listening.
Thanks, Larry. That was excellent. So
Thanks.
I want to start off with talking about sort of the importance of AI, kind of encapsulating a lot of what Larry kind of went over, some of the more technical deep dive aspects, and kind of bringing it back around to IT service management specifically. So, you know, Gartner really they've agreed with our sentiment where, you know, this is just too big of a phenomenon not to ignore, specifically for this industry. They've actually projected that by 2019, IT service desks utilizing machine learning and enhanced technologies will free up to 30% of support capacity. So just going back to, you know, what Larry was talking about, you know, improving your self-service performance, I think a lot of that's a really good use case for that. They recommend organizations invest in machine learning, big data, and other smart machine technologies to make current and future IT service desk operations proactive. So I want to get more into sort of the real-world applications of where AI can help to improve ITSM and specifically self-service for your IT service management end users. So let's start with the chatbot. So Dr. Hall just spoke a little bit about how chatbot was described as a near-term technology for maybe those who may have a question that may be a little bit harder to be found through kind of a simple search, or maybe it's just too confusing of a question, more nuanced of a question. It's just easier to ask it than to try to parse out the words and find it through search. So on the self-service portal, we at SunView, we saw the value in implementing conversational UI so that end users have a more natural, sort of a more engaging experience with the self-service portal. So this means you can ask the virtual assistant a question just like you would with a live agent, and the chatbot can intelligently parse the language using, like Larry talked about, natural language processing to deliver real-time answers, recommendations, stuff from KBs, data from announcements, FAQs, really anything that is pertinent to the question being asked by the end user. So, and over time, the system will get smarter the more people engage with it, the more data that's being trained to the system. And that's, of course, using some of the concepts that Larry talked about with the deep neural network that it's tapping into. So just recapping some of the benefits of chatbots, specifically for ITSM, the help desk, and the end user, the value is pretty clear. End users have quicker and easier access to the knowledge base, and can find solutions for low-level tickets faster than maybe a simple search functionality. Increased engagement of self-service impacts the help desk by reducing ticket volume, improving overall customer service, and of course increasing the efficiency of the organization itself. So I want to talk a little bit about image recognition. So this is kind of a new thing that we've been playing around with in our product. Right now it's more or less relegated to ticket processing on the staff side, but it could easily be applicable to end users and self-service. So using pattern recognition and machine learning, the service desk can actually analyze images and screenshots, maybe attached to a ticket or an incident, and run a similarity search to return results from other tickets that may have the same sort of error message. So the use case for this seems it's pretty clear. It's a really good use case for users that want to visually search KBs or staff that want more tools to resolve incidents more efficiently. And I want to end with sentiment tracking as another good real-world application. So I think Larry touched on this a little bit. When your chatbot, you're typing to the chatbot, the system can actually use the NLP, the natural language processing, to sort of gauge each touch point of the conversation between the end user and the technician, or in this case the chatbot. It really doesn't matter, to kind of figure out exactly, well, was this a positive interaction? Was this a negative interaction? How frustrated is the end user trying to solve this problem? And is the trend actually getting worse, or is it improving with each interaction? So you can actually really drill down into those interactions and then aggregate that data. And then the system can actually give recommendations to the staff user based on each of those conversational touch points to decide, hey, you should probably deal with these users first because they're more upset than maybe these users, and that way you can actually provide a more efficient customer service prioritization way of handling tickets. So of course that flows into self-service. It's all sort of a trickle-down effect where by being able to gauge the sentiment, the staff will be able to prioritize tickets and handle the most upset users quicker, and then we'll be able to improve customer service over time. And even some of that could reflect in improving the KBs that maybe didn't help a user in a certain instance, or improving or having new announcements. So just all of these things can help to improve self-service over time, as well as the overall fulfillment of incident tickets. So those are just a few quick examples of some of the features and applications that we're actually using and actively developing in our AI framework for ChangeGear, which is our flagship IT service management platform. And we sort of bundle all of these features and all of this AI technology in what we call Service Smart technology. So just very briefly, at the highest level, Service Smart technology provides IT staff and end users with smart recommendations for speeding up resolution times, provides relevant answers and feedback with intelligent search and predictive analytics. Also, there are ways for identifying critical trends that will help your staff and management teams to make better decisions on the service desk, and provide more engaging self-service with things like machine learning and chatbot assistance. Some of those concepts Larry touched upon earlier in the presentation. So here's just a really brief rundown. I'm not going to get too much deeper into it. If you want to learn more, I encourage you to take a look at what we have to offer at sunviewsoftware.com. And real quick, so just to kind of wrap everything up, we actually received critical reception of our platform. So Service Smart Technology received Pink Elephant's 2016 Innovation of the Year Award at their annual Pink Conference in Vegas. That was held beginning of this year. So if you're not in the know, maybe not up on all the ITIL and IT service management lingo, but Pink Elephant are actually longstanding luminaries and thought leader in the ITIL space specifically. So it was actually a pretty big honor for us to win this award. And I think that will close it out. So we'll get to the Q&A in a second, but if you have any sort of deeper questions, specific questions, comments, maybe personal stories regarding AI or machine learning, or even just self-service in general, anything really you've seen in this webinar, we want to hear from you. So feel free to either email myself at jspector@sunviewsoftware.com or Dr. Hall atlohall@usf.edu. And yeah, we'd love to get back to you and answer your questions. So with that in mind, we're going to wrap everything up with a Q&A.